Hello, welcome to our semiconductor education program. I'm Vincent Chang. I'm going to teach you about Class A output stages. Part 1, transfer characteristic. If you can remember, this kind of waveform corresponds to the Class A output stages. Class A output stage. The transistor, the key transistor of the output stage is fully on. The collector current of the key transistor is greater than 0 at all time. In other words, the conduction angle is 360 degrees. Look at the left-hand side. The circuit diagram of a Class A output stage is an emitter follower biased by a current mirror. Emitter follower. So Q1 serves an emitter follower, the base input, and the emitter output. The RL is the load. The current source is composed of a pair of transistor Q3 and Q2. For the emitter follower to function normally, the transistor Q1 has to be operated in forward active region. So similarly, for the current mirror to be operated normally, the current mirror transistor Q2 has to be operated in forward active region as well. So Q1 active and Q2 active. So if Q1 is in the active region, the large signal relationship between the output and the input has to be what? So look at the right-hand side. Let's try to derive the transfer characteristic of the Class A output stage. So VO versus VI, large signal transfer characteristic. Large signal, not a small signal, okay? So large signal transfer characteristic, VO versus VI. So if Q1 is in the active region, the relationship between VO and VI is simple. So VO equals VI deduct minus VBE1, large signal VBE1, which is around 0.7. So the relationship is a straight line, right? It's a straight line for the relationship, to describe the relationship between VO and VI. So it's the linear region. So it's in the linear region. So VO, when Q1 is in active region, so it's a linear region. Now, let's focus on the VO. So when VO goes up, because when VI goes up, VO goes up, right? So when VO goes up, then what happened? The VCE1, the large signal VCE1, where it goes what? So when VO goes up, and the VCE1, because the VCC on the top, the ceiling is fixed. The ceiling voltage is fixed. So VO goes up, and then VCE1 goes down. Right? So when VO keeps going up, and VCE1 goes down. So what's in your mind? So let's look at the right-hand side. The IC versus VCE, the output characteristic of the key transistor. Okay? So IC versus VCE, VCE1. So when VCE1 goes down, the green arrow. So when VCE1 goes down, then it moves toward what region? Move toward the saturation region. So it has the tendency to leave the active region and go into the saturation region. So what happened? So at this point, the green one, right? The green point. So look at the green point. So the green point is the edge of saturation. It's the boundary between active and the saturation. So once it arrives the green point, then the the Q1 is in the boundary between active and the saturation. Okay, so at this point, VC1 is approximately equal to 0.2 volt. Okay, so for the simulation, it's the 0.219 volt. Okay, so 0.2 volt, and let's say the VCC is fixed at 15 volt. Then, so what's the value for the output voltage? Would be 14.8 volt. So this 14.8 volt is equals to 15 deduct 0.2 volt. So this is what we call the V capital M, denoted by V capital M is VCC, the positive saturation voltage equals VCC minus VC1 saturation. Okay, so the conclusion, to sum up, the positive saturation voltage is close to a supply voltage and also determined by, is limited by the saturation of Q1, the saturation of the emitter follower transistor. So now let's look at the other direction. So let's say if VO goes down into the negative direction, what happened? What happened? So let's look at, I think naturally you would think about, okay, so in the positive direction, it's limited by the saturation of the upper transistor, right? So in the same way, so in the negative direction, it will be limited by the saturation of Q2, the current source transistor. So for the current source to function well, of course, it has to be in the forward active region, right? But once the Q2 enters into saturation, so it will give us another limit, which is the negative saturation voltage denoted by V lowercase m1, V lowercase m1, Vm1. Okay, so the answer is very similar to the positive saturation voltage. So it would be negative 15 volt and then potential rise, the potential voltage rise. So negative 15 plus 0.2 volt will be negative 14.8 volt. Easy. So this is the expression for the negative saturation voltage, negative VCC plus VCE2 saturation, okay? So now I want to consider let's consider another scenario. Let's say if the load resistance is 1 kilo ohm, you can try to take the note, okay? So think about this. If load RL is 1 kilo ohm, let's say if the reference current, the bias current is 10 milliamp. So 1 kilo ohm of the load resistance, 10 milliamp of the bias current. Do you think the negative saturation still be negative, the same, will be the same? The negative 14.8 volt? Will the answer change? So the question is, when RL, in this case, just look at the circuit, okay? Look at the circuit. So if RL is 1 kilo ohm, RQ is 10 milliamp. So what's the negative saturation voltage? What would be the negative saturation voltage? So I want you to pause for 5 minutes to think about this. So what would be the negative saturation voltage in this scenario? So let's pause for 5 minutes. You got it? So what's the answer? The same? Let's see. If this is the answer, okay? If this is the answer, then what happened? 14.8 volt, then there will be a current 14.8 milliamp, 10 milliamp. So there will be, the rest of the current will be 4.8 milliamp going upward, okay, against the arrow, all right, against the arrow, okay. So this is impossible. This is ridiculous. This is impossible. So the answer will be, in this case, the answer will be negative 10 volt. In other words, it's impossible for the swing, for the output voltage go down to negative 14.8 volt. No, it will be limited around negative 10 volt. Why? So when it arrives negative 10 volt, the current will be what's the current of the red current? 10 milliamp. So 10 milliamp, 10 milliamp, 10 milliamp, 10 milliamp. So what's on the top? What's the current on the top? 10 milliamp, active, still active, 10 milliamp. So 10 milliamp, so what's the current on the top? 0. So which means the Q1 has no current. So what's the mode of operation when there's no current flowing through the transistor? Cut off. So the negative saturation voltage will be limited by the cutoff of the emitter follower. Will be limited by the cutoff of the emitter follower. So here's the answer. So in this scenario, the negative saturation will be around negative 10 volt. And determined by, limited by the cutoff of the emitter follower. All right? So Q1 cutoff. So the expression for the negative 10 volt, so you can get this answer. So negative 10 equals what? Equals negative IQ times RL. So the 10 volt IQ times RL. All right? So negative 10 volt. So you see the difference, right? You see the difference? Two different scenarios. On the left, the first scenario, limited by Q1 saturation. The answer, negative 14.8 volt. On the right, it could be limited by Q1 cutoff, and the negative saturation will be negative IQ times RL. So here's the takeaway. The first takeaway is very simple. The positive saturation voltage will be limited by the saturation of the emitter follower transistor, right? So here's the positive saturation voltage, VCC minus VCE saturation. So 0.2 volt, 15, 0.2, and 14.8. The second takeaway, the negative saturation voltage will be a little bit complicated. Okay, so two scenarios. So it totally depends on the combination, the data between the load resistance and also what the bias current, IQ. So the first scenario, it will be limited by the saturation of the current mirror transistor Q2. So here's the answer, the negative VCC plus VCE saturation. But on the other case, another scenario, so it could be limited by the cutoff of the emitter follower transistor. And the answer, in this case, is for the negative saturation voltage, here's the answer, negative IQ times RL. So to sum up, the two takeaway gives you the idea about the positive saturation voltage and also the negative one. All right? So I hope you learned something from this lecture. The large signal transfer characteristic of a class A offstage. Thanks for watching.